Okay.
Welcome, everyone. Thanks for being here. Thanks for watching. And I'm happy to be here to welcome Professor Susan Murray to speak about her topic. I'll let her tell you the title. I'll just tell you a little bit about her. She's a professor in the Department of Biostatistics here at the University of Michigan with expertise in developing methods for event time data. She balances her methodological work in the field of biostatistics with pulmonary research collaborations, holding a joint appointment as Professor of Internal Medicine in the Division of Pulmonary and Critical Care Medicine. Dr. Murray has served on editorial boards for biometrics, lifetime data analysis, and the American Journal of Respiratory and Critical Care Medicine, and is just beginning her term. Welcome as president of the Ann Arbor chapter of the American Statistical Association. Please join me with welcoming Professor Murray for our talk.
Thank you. All right. It's good to see you, and I appreciate you as I learn the ropes of recording these meetings on my laptop. So this is work that, I did with a PhD student, Yizhua Wang, and she's now, graduated and working in industry, but she is absolutely critical in me being able to tell you this information today. So this is all meant to be pitched at a level where you can get the idea of how to do what the models are trying to do, how to interpret results, and even program some of these. So I'm hoping it's like a how-to kind of discussion. There's some source material. The topic is called Tau-Inflated Beta Regression Model for Estimating Tau-Restricted Means and Event-Free Probabilities for Censored Time to Event Data. And there's some source material here. The first link is to the article. I'll be posting these online. The second link is software that Yizhua wrote that can reproduce all the analyses that appeared in the paper, including simulations. So the journal, biometrical journal where this article appears, makes sure that they can reproduce all of your results in every table and figure. So it's all there. But for us, I have a GitHub site here that Yizhua put together just for us that has, the more user-friendly code on the talk. Okay. And somebody here in the room will probably know exactly where to post these files so that you all have access to them. Okay, so the goals are to start off from a more well-known model, although it's not known to everyone. There's a model called the Tau-Restricted Mean Survival Time Regression Model. And the intent is to model Tau-restricted event time. So the technical way we might write that is the minimum of Tau, which is a user-selected parameter. It might be the end of your follow-up time, like the largest event time in your data set, or you can even choose it to be 1 year, 5 year, whatever your data supports. And then the event time of interest that you want to understand. And so I'm going to review that and how to get R code for that in case you haven't used the model in a while, just so that you have it there. And then I'm going to motivate what brought us to coming up with this tau-inflated regression model. So we're calling it tau IBR. Oh, I missed the word beta, tau-inflated beta regression model. And it's based on this fundamental identity that rewrites how we think of these restricted event times. So I'll spend more time on this later, but whenever you have a minimum of two things, it's the smaller if it is in fact the smaller thing, right? So this is tau times the indicator that the event time you're interested happened after tau, plus the event time you're interested if in fact it happened while you were following people up less than tau. And just by the way I've written this, you can sort of see two random variables emerging. One is the one you're interested in, and the other is a Bernoulli that you made it to the end of the follow-up period of duration tau. And so I've done that intentionally, and we'll come back to that idea. But in my view, this opens up this idea of a mixture distribution that's behind the scenes. Who makes it all the way through follow-up, and what characteristics drive that? And amongst those who don't make it all the way through follow-up, are there features that give people more or less attractive events? So I'll describe the tau IBR model in terms of, how we define the model and how we get restricted mean survival time estimates, interpret parameters, all that sort of stuff. Show you intuition of, when it's good to use the model through simulation. I won't spend too long on this because it's not always interesting to people to just see simulation results. And then I'll show you how to do some of these analyses with code. Again, knowing that you'll have access to this online so that you can copy and paste and play with your own data sets. So I just want to review a little bit about restricted event times. And we work with these event times nearly always. We don't call them restricted event times, but in most grants, in most studies, we're only able to watch people a finite period of time before our money runs out or our interest runs out. And so we are always in this situation of observing the event time while we're following people. But if we don't observe the event time, you certainly observe how long they lived. And so, so we've been analyzing these forever, just not thinking of them as a mixture of the event times and a lifetime length tau. So suppose that you think of tau as the largest observed follow-up time. And this is the usual Kaplan-Meier kind of curve that you see. And so you can sort of see that you have information on, when people were having events in this little pretend data set. But there's a lot of information here about the people who never had the event during this 4-year window follow-up. And so we spent a lot of time trying to model, what's causing these events to happen at speed, but we don't spend as much time modeling this point estimate. And, if it was all observed data, you could do so with logistic regression. With censoring, it's a little bit more complicated. But the point is that there's a mixture of information here that we need to pay attention to when we're thinking about these restricted event times. And in terms of this Kaplan-Meier estimator, if you're just talking about the follow-up period where you have data, the Kaplan-Meier estimate that we usually think and write about when we're teaching or analyzing our data is equivalent to the Kaplan-Meier estimate for this restricted mean. The only difference is that at tau, if you really define it as the minimum event, the curve goes all the way down to the bottom. But if you look at things like area under the curve, it's the same, whether you're talking about the random variable of interest or the tau restricted variable of interest. And just as a reminder, if you look at the area under the Kaplan-Meier curve, that is a restricted mean, right? So the area under this curve is the amount of time on average that you are event-free during this 4-year follow-up period. And so there's a really nice model. It's easy to use, it's user-friendly, and you can interpret results well, called the tau RMST regression model, where RMST is restricted mean survival time. And it's the most well-known of these. There's a lot of different versions that look similar, but this is one that I particularly like, introduced by Anderson, Hansen, and Klein in 2004. And I've put a simple version of the model before, a simple version of the model here with just an identity link where you've got this restricted event time here, and you model the mean of that restricted mean survival time in terms of covariates. And you can actually use any link function that you want, but for simplicity, I'll just keep it to the identity link for the purpose of this talk. And so if you do a regression model, this is going to estimate the expected event-free years during the tau years of follow-up using covariates. So you're no longer in the situation where you're integrating under a Kaplan-Meier curve. You're actually modeling this mean tau restricted event time with covariates. And this paper by Anderson, Hansen, and Klein defines something called pseudo observations. And it's a beautiful tool. And it's an approach to estimating model parameters when you really do have censoring, but you want to use methods that were really developed for uncensored methods. And I'll say a bit about it on the next slide there, but once you have these numbers, these pseudo observations, you just use them instead of the event time that you may or may not have observed completely in the model fitting process, and then use standard regression models. So the way I wrote this, you could just use a linear model, but you can also use generalized linear model software to get parameter estimates if you have different link functions you're using. And so it's a little bit magic that these pseudo observations are based on observed data, and you can use them just as a single number and do analyses, even though you have really censored outcomes involved. And if you haven't heard this trick before, it's useful for so many things. So identity logarithms are both in common use. So I'm guessing that pseudo observations aren't known to everyone, but the idea is that you have, for every individual in the data set, a pseudo observation, and you really want it to come back to something similar to the event time. And so the intuition here is that you take n times the restricted mean survival time that's based on the whole cohort. So this is like an area under the Kaplan-Meier curve from the whole cohort. So n times that mean, and then subtract out n minus 1 times that same calculation, but with person I removed. So both this RMST and the RMST minus I are non-parametrically calculated using area under Kaplan-Meier curves. It just depends on whether it's the whole cohort or the cohort that's removed person I. And that's the number that you use. And it turns out that, if you have completely uncensored data and you do this calculation, you actually do get min tau ti back for that person. If there's no censoring in the data set at all, the area under a Kaplan-Meier curve is going to look just like the X bar for min tau ti.
So you're taking the area of one and subtracting the area of another one with that one being removed. Sorry. Never mind.
I think you have your mic on. That's probably.
No, my mic's muted.
Oh. Okay, it's me. So yeah, this is an area under a Kaplan-Meier curve, but it's multiplied by n. So if this looked like an X bar, the way it would with no censoring, it would be basically the sum of the X's for everybody. And then this one, when multiplied by n by 1, would look like the sum of the X's when you have everybody but person I. And that difference would turn out to be the XI or whatever the TI here. So if you have censored data, there's some real cool intuition for why this works. And if you have censored data, you really are trying to estimate the same thing with these area under the Kaplan-Meier curves. And the authors, showed that. So what happened that's different that now I'm echoing? All right, that when you use these pseudo observations, that you have the same conditional expectation as the potentially censored min tau ti outcome that you actually don't have to use in regression. And so it's a very nice result. And it kind of opened up a lot of easy transitions to analyzing censored event time data using pseudo observations and applying them to methods that were meant for completely observed data. And there's been a long list of papers that have come out, including ones that I've worked on since 2004, making sure this works in various situations, but the intuition is always bearing out that this works well. And just to, make sure this is super clear, this is the model that you would want to fit if you didn't have censoring. And somehow, even if you have censoring, this will give you the very same parameters here on average. The conditional mean given the covariates for this random variable is the same as this conditional mean given the same covariates. And so you'll get, similar inference, even if you work with the POIs. It's very, very cool. And I use it a lot. This is actually a jackknife methodology approach for those who were trained in the time when jackknife was a big part of our literature. And it's just a version of jackknife for this kind of setting. All right, so, and here's just the formula for the pseudo observation again. And I wanted to just have a note that because you have an area under the curve for the whole cohort, and you have an area under the curve for the cohort without person I, there you have to think about the maximum possible tau when using pseudo observations. And it has to be a valid choice for estimating all of the area under the curves for every single person in the data set who's removed. So if you remember, when you have a Kaplan-Meier estimate, it's only consistent when you have someone at risk. And so this person without person I, it could potentially have a smaller follow-up period than if you added that last person in. And so you have to think about how that affects your upper limit of integration for these Kaplan-Meier curves that you're using. And so the really thing that you have to think about is that at least one of the two largest event times have to be included in each of these RMST minus I's. So when figuring out the maximum possible tau, you only need to think about those largest two values because at least one of them will be included. There's no restriction on tau if the largest two event times are both deaths because these curves go down to 0. And in fact, you might be looking at means, not tau restricted means. If both of the largest two event times are censored, then the maximum possible tau is the smaller of those two values because you'll have data support through that time point for each data set where person I is respectively removed. And if only one of the largest two event times is censored, then the maximum possible tau is that value. And you're going to increase your upper limit of integration to be as big as possible. This is what you think about when you're applying this method. And so for an application, I have this azithromycin for prevention of chronic obstructive pulmonary disease exacerbation trials, which I'll just call the azithromycin study probably for the rest of the talk here. And it's a data set where they really wanted to know if azithromycin extended time to exacerbations in these COPD patients. And so the primary endpoint was time to first acute exacerbation during the subsequent years. So think of tau as a year. That's how long they followed these participants. And it turns out that if you're looking at tau of a unit of 1, you can interpret it in a cool way. So generally, a 1-year RMST model would estimate acute exacerbation-free days over the follow-up year by treatment group and other patient characteristics. But you can also interpret parameters as the absolute increase in the percent of an exacerbation-free time that's lived during the 1-unit follow-up period. That corresponds to a 1-unit increase in the predictor. So having a scale from 0 to 1 for your outcome, instead of just thinking about it as a time unit, you can think about it as a percentage of exacerbation-free time. And that comes up later when we go to the tau IBR model. So there's an advantage of rescaling outcomes from a 0 to tau scale, or for your grant, you can still rescale it to a 0 to 1 outcome. When you're interpreting results, if you want to write about percent exacerbation-free time during follow-up. And so the data set is going to be posted, and the variables are, the usual X and delta variables for the follow-up time on study. And if delta is 1, there was an observed exacerbation. And then there's a bunch of covariates. So we'll be focusing on the treatment azithromycin variable. But there's a bunch of other variables here: age, gender, something about their pulmonary function, whether they're current smoking, and some site indicators. I'm largely going to submerge the site indicators because they're not interesting to look at, but they're in all the models as adjustment features. And of note, I've centered all of the continuous variables around some useful, interesting value for the cohort. And that was done intentionally to use with the tau RBR models. So the data kind of looks like this. So these are really censored ages and censored pulmonary function values here, but this is kind of what the data looks like, excluding the side indicator variables. And so the restricted mean model gets loaded with this pseudo package, and the regression is very straightforward. You just put in your X, your delta, your tau to create your pseudo observations, and then you can use these pseudo observations for whatever you need. And so this is what the pseudo observations look like here. And so I do have this note here that pseudo observations have the same conditional expectation as the uncensored data values would have, but they don't necessarily look like the uncensored outcomes of interest. They can be, the pseudo observations can be smaller than the lifetime you actually observed. They can be greater. And so they can't really be used to plot like individual level data. It's not attractive. They're not, for instance, if you think of imputing missing values, that's not what the pseudo observations are doing. But on average, if you use these values to build these regression models, the parameters will be correct. All right, so then these numbers get used as an outcome in these other models. And so here's just I've put the pseudo observations divided by tau, so I'll have a 0 to 1 outcome scale approximately. And I've got these other covariates now that I'm putting into the model to understand what happens. And here's the output from this just regular regression package with estimates, standard errors, p-values, all the rest. And so all this is just really easy to use in standard software these days. And so if you wanted to see the effect of azithromycin, you had this identity link here. So on average, you lived, 9% longer, in absolute difference, longer during the year of follow-up if you were taking exacerbation-free if you were taking the azithromycin. And I have a sentence coming up just to, make sure that that got across clearly. This is just some code to get manuscript-friendly results so that you have, the effect size, the confidence intervals, and the p-value. So I won't go through the details, but that gives you kind of the manuscript-worthy looking table. Here it's typed up a little bit prettier, and I'm focusing on this treatment result here for this talk. And so during the year-on study, the percentage of time spent exacerbation-free was estimated to be 9.1% longer when taking azithromycin versus placebo. And then the usual things that you give, like confidence intervals and p-values and so on. All right. So that's the standard restricted mean model. And
here, age was a continuous variable, the binary variable.
it's continuous. It's continuous, and it's centered around. What did I say? 65. Thank you. Yeah. And so this is, and it's per 10 years, the effect. So for every additional 10 years of age, you lived about 3.5% longer exacerbation free during the period. So you kind of get everything is kind of nice with the same kind of interpretation of how much longer you lived during the year. And so you can sort of see the relative impact very quickly too, for these. So it's attractive. I've been using these models for years. I think I had a talk with Klein pretty soon after he figured out the pseudo observation trick, and I've been like riding on his coattails using his brain for how awesome the pseudo observations work. Okay, so what is this tau inflated beta regression model, and why am I interested in it? So I mentioned this fundamental identity earlier, and writing it this way, and it's a mixture random variable that can be written in terms of a Bernoulli. So that's this indicator that you didn't experience the event through the tau period of follow-up, and it has its own mean, right? And this other random variable yi, so it's the event time you're interested in divided by tau, so I'm keeping it on the 0, 1 scale. And it's conditional. It only ends up being this value if you had, this ti less than tau. So y is a conditional random variable. And for this model, we're trying to model something continuous between 0 and 1. So we assume a beta distribution for that, which is a pretty flexible distribution. And its mean is this mu y that we'll be modeling. So when we look at this BI, we're going to be thinking kind of like a logistic regression. And when we think about this conditional random variable yi, we're going to be thinking about a beta distribution. And so the random variable min tau t, when you write it in terms of these two random variables, looks like this. So it's clearly looking more and more like a mixture distribution. And so that it suggests modeling each of these components of the restricted mean separately, potentially using different covariates when we're modeling BI as opposed to YI. Okay, so for the component BI, this indicator that they went throughout follow-up without having the event, we build some kind of a logistic regression model. We'll have to fix up the fact that we have censored data with our estimation methods, but for practical purposes, once you get the estimates from the correct method, you can interpret this just like you would any logistic regression model. And so you're kind of saying what individuals tend to be event-free during follow-up, and that's kind of what you're trying to get at with this part of the model. And for the beta regression model, so that's the Ti over tau, given that they actually had the event, I'm modeling this. It kind of looks like logistic, except this is based on a beta, not a Bernoulli. And so when you're thinking about this component of the tau IBR model, you're saying amongst those who have the outcome during follow-up, what individuals have a higher percent of event-free time?
Question?
Mm-hmm.
Yes, I've never done beta regression. It looks like the logit link is used for beta regression in addition to.
So beta is between 0 and 1, like that outcome is between 0 and 1. And so you don't have to, you can use any links you want, but it has the same advantage of having means between 0 and 1. So they use the logit link for Bernoulli's to have probabilities, the pi i's between 0 and 1. And the mean of a beta should also be between 0 and 1. So people use the same kind of link to keep that algebra in a healthy range when you're estimating the mean. But you don't have to. You could use identity links, and if you're not close to the edges in your cohort, identity links work fine.
So on the software, you're doing logistic regression for beta distribution. You have like link equals logit, dist equals beta, instead of dist equals Bernoulli.
Yeah, I have to tell you that Ishwa did all the programming in R, and I think she had to program everything because she was modeling these jointly. So I don't know what you would usually do for beta regression, but if there is an option for dist equals beta and link equals logit, absolutely. If there's an option like that in GLM, that'd be fine. But you're only modeling one component of the model, and Ishwa's code is fitting these kind of as one big system. So this framework achieves a couple of important goals, and one of them is that it directly addresses the point mass at tau for these min t tau random variables. And if the goal is tau restricted mean estimation based on covariates, it's addressing that you have a lot of information about their tau restricted mean, right? If people hit, if you can model that probability that they survive past tau, that's a big part of bounding where your restricted mean event times can be. And you can get that straight from the model. If you have estimates for all of these parameters that come from these two models, according to the covariates that are used in the two models, then you can estimate that pretty well. And notice I've intentionally labeled these covariates differently. You don't have to have the same covariates in the two models. So in fact, I would suspect that most of the time you have quite different covariates in the two models. And we'll see that when we go back to the azithromycin data, which things look like they're statistically important. It varies in the two models. So this system also addresses the possibility that different covariates may play a role in these two models. And if you just use the restricted mean survival time model, you've got the covariates are just doing one thing. They're modeling that mean and they're not divvying up, who are people who are susceptible to having the event and who are people who maybe aren't sick enough to have the event. They're not separating out those two ideas when they're putting everything in this one model. So interpreting coefficients for the part of the model that deals with the Bernoulli is just like logistic regression. So that's not a new skill set. This is just the typical interpretation that e to the beta is related to an odds ratio when you increase the covariate from z to z plus 1. So this is familiar territory if you use logistic regression. It's just that our results will be adjusted for the fact that you had censoring. For the beta, the interpretation is a little bit more complex. And so we have it kind of written down here. If you increase a particular covariate, like the kth covariate from z to z plus 1, and all the other covariates are set to 0, the fold change for that mean is this formula. And so it involves both the intercept and the parameter for the covariate you're looking at. And the formula would be more complicated if you had all the other covariates non-zero. So we simplified it so that if you feed in data that's been centered around a point of interest, this interpretation of the fold change here will be, assuming a typical patient profile that has kind of these zeros. And so it's helpful to set all the covariate reference values to 0 so that you can interpret this fold change a little bit more easily. And so the censoring is addressed by fitting models using one of two approaches. And sadly, we were not able to, or we didn't, maybe we could have figured this out, but we didn't use pseudo observations. So we used, approach one was to do estimation maximization to handle the censored nature of the data. And approach two was to do inverse transform multiple imputation to fill in the missing information for the censored outcomes. And both of these methods work pretty well. Depending on when you went to school, you might be very familiar with estimation maximization. And if you really love reading technical details, they're all there in the paper for what was done. If you haven't seen this inverse transform multiple imputation method for filling in data, the basic idea very quickly is that you have different risk sets of individuals for each censored person. And so you find risk sets of similar individuals to the censored individual that you'd like to impute. And for this model, we're looking at the parameters from the two components of the tau IBR model, seeing if they're similar. And so once you have that group of people who are similar, at least with respect to these mu I pi I, you estimate a Kaplan-Meier curve within that subgroup, and that Kaplan-Meier curve is used to impute an outcome for how much longer they would have lived past their censoring time. And so it's a very cool little method. I know I'm not giving you lots, but I thought I wouldn't have time to talk about that much. If you are interested, next month's speaker is going to be talking about a version of this imputation strategy for bivariate censored outcomes. So you'll see more. So once you get all of the censored people's residual lifetimes imputed, you do that m times. So you get m data sets to analyze and parameters and things from each of those data sets. And then you combine them using Rubin's rules, which is a very natural way of averaging parameters across the data sets, but then also fixing up the variance of the analyses that happened with the various data sets. So I've omitted the technical details, but both of these methods work pretty well in terms of estimating parameters, estimating restricted means of interest when you have censored data. And I won't bother showing you the simulation results on that. One nice thing is that when you're using this multiple imputation approach, you can do additional analyses and plots. And I'll show you one of them. So I did want to show you one thing that we found interesting through the simulation. Looking at the restricted mean survival time model that I love, and then this new model that I also kind of love. And so we generated some independent covariates, uniform, Bernoulli uniform. I'm showing you a large sample size with tau of 30, but we did lots of sample sizes. I just didn't want to show you a multi-panel plot on a screen that it would be hard to see. So I'm going to show you the results for the 1,000. And then we had a logistic regression model kind of set up for the BI random variables and the beta regression model for the Y random variables. And something that I just want you to notice is that, we have some of the same covariates in these models, but the logistic model has an extra one, and so some of the same information is helping predict these different outcomes from the mixture. Yeah.
And why the beta regression has a constant term of -2?
Oh, so you get to pick, the probability that people are event-free. And this is going to help with that. And you get to pick what percentage of time people live event-free if they have the event. And the intercept is kind of helping with that. So they don't have to be the same number because they're different events. So we just pick numbers, they look round because we just picked numbers, and we tried to set up a situation where 52% of the simulated individuals would have lived all the way through the follow-up period if you observed those values. And of course, since we simulated them, we knew kind of how that was going on in the background. And then we had independent censoring so that at least 30% of the individuals had censoring prior to the end of follow-up. So we tried to have both. This first bullet is just making sure that in simulation we had a healthy number of people to predict the BI part of the model. And here we wanted to have enough censoring to test that the censoring fixes were working properly, And this is one of about a bajillion simulations. After the review process, we had many more requests for simulations, and they're all in supplemental materials. So this is just a representative one. And the reason I wanted to show you this is this key finding that we found really interesting. And that was that, both of these models would give you unbiased estimates for the restricted mean of interest, right? But the tau IBR model gave restricted mean estimates that were more precise and had better coverage probabilities than the original model. And so in this graphic, all the 1,000 subjects are being shown here on the x-axis. So each dot is a person, and the value on the vertical scale is the difference between the estimated restricted mean and the true one that we use to generate the data. Okay, so the closer you are to 0, the better the model did for that particular person. And so you expect, this is all individual level data, so you expect a lot of variability here. And each of these methods allows you to have a confidence interval, a 95% confidence interval, for the true value. And so we kind of split up the dots into outliers where the confidence interval from the method didn't overlap the true data value, and values where they did. And we also have them split up by color if it was an estimate based on the tau IBR model or an estimate based on the tau RMST model. So there's a lot here in this one graphic, which is why I only wanted to show you one of them so you could just see this one graphic. And so all the blue and the green, they had their confidence intervals were covering their actual data values. So you think of that as a good kind of performance. If you look through here, though, you can kind of see that the spread of the green is a little bit more narrow vertically than the spread of the blue, right? So the difference between the observed and the expected is a little bit bigger for the blue, and that's the original model. Also, for outliers, with 1,000 people, you expect for a 95% confidence interval that you would have, 50-ish people roughly that would be outliers. And so for the tau IBR model, there are these orange triangles. And so by eye, which method has more outliers?
So I have a question about the blue. That looks like it's an RMST.
Yep. The blue are people's, from the RMST model, it's the difference between the truth and the estimated RMST.
That
And-
looks like it has a small compared to the other.
Oh, well, so the blue and the green are where the model did a good job. And so everybody here, you know, in those blue and the green, the model did a good job. And they're centered around zero. Both of these methods are unbiased. The average is around zero for these kind of places where it's doing well. So the places where the model isn't doing well are the orange and the pink. Okay, so these are all the places where the difference between the fitted and the true was pretty big, and the confidence interval for the method didn't cover the actual truth that generated the data. Okay, so, and there's by my eye and by count, if you look at the tables, there's a lot more pink here. So there's a lot more variability in tau RMST estimation than in the tau IBR estimation when we looked at this. And we thought, well, does this go away with larger sample size? You know, and this was the 1,000, but we looked at 100, 500, 1,000, 1,500. This phenomena doesn't go away. It's not an asymptotics issue. But it does go away if there are no important covariates in the logistic component of the tau IBR model. So if there's no important covariates in that point mass tau model, then the models perform very similarly. But if there are important covariates that show up in that point mass of tau model, then the coverage probability for these restricted mean estimates aren't really great using the older model. So I don't think you get science too wrong, but you get a different level of information and there's more precision in these estimates. So I want to kind of take out this new model and apply it to the Azithromycin study so you can see what we learn when we use the new model in this data set. And one feature, remember, of this model is that when we do the multiple imputation part, filling in the censored data, we kind of get a bunch of imputed data sets where min tau t has been completed. And that allows us to kind of make cool plots using the methods available for uncensored outcomes. And so I am kind of in love with heat maps at the moment. Heat maps are like, if I can come up with a way to use a heat map, I'm just like all over it. And look how beautiful this is. So this is looking at the min tau ti values averaged across 10 multiply imputed data sets. So it's censored event time data, but we can kind of look at it by, averaging for the censored people, averaging across their imputed values for those people, then using the observed people for the people who didn't require imputation, and kind of just look at the raw data, using a heat map, which I really love. So you're not just, fitting a model and interpreting the model. This is the raw data to the extent that we can look at it using this. Oh, I touched something and it went away.
It's always healed itself so far.
Ah, good. All right. And so the way heat maps kind of work is and don't ask me any deep questions because this is all Ejois programming and talent, but you can specify predictors on the side here. And in addition to their outcome, which is kind of this bit, you can kind of color code some categorical variables on the side and kind of see, do some clustering and see what's going on. So there's some kind of clustering that's going on here. And the heat map here is the legends down here. So shorter exacerbation-free days are in the darker purplish range and longer exacerbation-free days are in this yellowish period. And so it's kind of clustered the people up here who have the shorter event-free days. And so you can kind of look at that and sort of see what's going on here. And right away, the treatment colors are the closest column. And you're sort of seeing a lot of blue here, and blue is placebo. Oh, is that? Oh, gosh, I have to use this thing. I thought my cursor would show that. Let me see. So for those in the room, all right, so this is I've been pointing with my cursor this whole time. No, that's okay. So these are the people who had the shortest exacerbation-free days during that year. And if you look at this nearest column over here, that goes with these treatment groups. And you can see there's a lot of blue up here that the people taking placebo were having the shortest exacerbation-free days. And this is not based on a model, because even the imputation is fairly non-parametric once you get a risk set of people similar to the person that needs the impute. And so you kind of get a look at the raw data here. And, you know, there's this column too, gender. I mean, you could look at all of these if you wanted to, but just peek at gender, and the people who do the worst are the women. You know, you can just kind of look at that visually and see more of the dark blue here than the yellow. So I just love that visual, and you can always do something cool when you multiply impute data. So here's the specification of the model, and there's not a lot of thought that went into the covariates here. These were the covariates that were used in the main science paper that was published, and I just threw everything into both models just to see what happens. Okay, so treatment's the one that I've been focusing on, and when you get the fitted results, you know, these are kind of what the values are looking in the model, and we'll spend some time interpreting the treatment variable for each of these and see what we learn. And hopefully you can see this a little bit here. So let's focus first on this beta regression model. That's for the Y's, right? And so I have a fold change here, confidence interval and p-value. For those of you who like to double check math, you know, this is how we got the fold change with the algebra using the parameters from the previous page. And then this is the sentence that we use to interpret. And so amongst those with exacerbations during the year, azithromycin did not significantly increase the percentage of exacerbation-free time during that period. And I think this is for multiple imputation because I used those numbers. So the fold change of 1.022 longer exacerbation-free time comparing azithromycin to placebo and adjust for other factors of the model is the point estimate with confidence interval and p-value here. And so this part of the tau IBR regression model doesn't see a treatment effect, even though we know there is one based on the traditional model, right? But it's not about extending the amount of exacerbation-free time amongst those who are susceptible to having these events. And if you look at the other predictors, the only one that really affected the percentage of exacerbation-free time amongst those who had the exacerbations, it was age. That was the only one that was significant, and the rest, no. So when we look at the model, the logistic component for the B's, you know, there's a lot of significance down here. Now that's where all the action in the model is happening. And here's the treatment one. So it's the usual odds ratio interpretation. So you have e to the beta from the treatment coefficient from the last page. And so the odds of remaining exacerbation-free at 1 year were significantly higher when taking azithromycin versus placebo, adjusted for other factors in the model with the summary statistics here. And so it looks like azithromycin is making people less susceptible to having the exacerbations. It's not extending the time to exacerbation necessarily in a significant way if you tend to be one of the people that's really susceptible, but it's helping you make just overall less susceptible. And so I wanted to show you what this looks like when you choose different values of tau. So we've been focusing on this value of tau of 12 months. If you look at different versions of tau, you get kind of a similar message. This is the restricted mean times to exacerbation. This is using the tau IBR model, but you're also seeing that azithromycin really is having this longer average time to exacerbation in months when you're looking at the first 9 months of follow-up, when you're looking at the first 6 months of follow-up, and so on. And 3 months, it hasn't had enough time to do much, but it's heading that way. And most of the signal is coming from this logistic part of the model. So this is again for various choices of tau, the probability of being exacerbation free if you're on azithromycin versus placebo, and the rates as you vary the choice of the follow-up period you're really studying. And if you look at amongst those who have exacerbations, is treatment giving you a longer period exacerbation free, it really is right on top of each other. And these are all on the scale of percentage, so it's not changing much, regardless of how you look at tau. All right, so
Weren't the fold values for the other variables large as well?
yeah, I only showed treatment just because I wanted to focus on one thing, and it's already like 655. So I was trying to,
Okay.
but yeah, but absolutely, you can interpret the other ones as well. And so in terms of the software for the tau IBR model, there's a GitHub site that is linked in here. So when these are posted, you'll be able to go to this. And there's a data set that I used for today. And then these are the big functions that Ijwa has put together. And then you create your own little script file, of course. And then the following code should work. She was programming with RStudio, so there might be RStudio things that are involved here, but I tried to tell her to narrow down the number of libraries to load, because I think she just has this thing where if she ever uses a library, it never gets deleted. So I'm not really sure which of these are essential, but she put them all, she likes to be complete, so she put them all in there. And she also, because she is not a professional programmer, she has this little thing of no matter what the warnings are, just keep going so that you'll get your results. So the key for using the code is to have the variable names exactly the way she uses them within the packages. So you need to call your event time X, your censoring indicator delta, and then she needs you to pack the covariates for the model, the mu model, and the covariates for the pi model. And so these are just the covariates that are being called Z mu. And then I copied the same thing into Z pi, but you can change this part when you're using it for your own data set. And she kind of needs this end subject. All this stuff has to get run. And then this row underscore MI is telling you which people need to have their censored value imputed. And then this is kind of like just copy, paste stuff. There's nothing here that you need to edit. This is getting you all the results, and it's sort of telling you what you're getting here. And so sorry if I'm clicking really quickly, but you just have to run that page as is. And then here are the results. This coding again is just run it as is. You don't need to change it. And it'll give you the results from the beta model, the pi model, and all the coefficients and the variance estimates here, and the results from the mu model with the coefficients and the variance estimates here. And then she's got script also for how to get the fold change. And she's done it for one particular predictor, the treatment predictor. So I've got like treatment in yellow here, and that matches the second entry of the covariate matrix. So everywhere there's a 2 here, you can switch that to different covariates to get the fold changes that she has in her output. But you just run this as is. The only thing that you would change is which covariate you're talking about with these 2s. And this is the fold change information that she had tabulated. Here's from the logistic regression part of the output. Those covariates were the 13th through 17th in the joint matrix of the covariates for the models. And so that's the only part that you would have to edit, which are the covariates that apply to the pi model. And then the results are kind of displayed as estimate, confidence interval, p-value down here. So everything is kind of laid up to be user-friendly, but because it is a student, former student, PhD graduate, but a program, if you run into a glitch, I'm going to throw her under the bus and say, contact her. And I've had my graduate students contact her many times when they're trying to use this. So in summary, this is a model, this tau IBR model should be considered if you're modeling a cohort of participants, and a lot of them are event-free at the end of follow-up. So if you're seeing all the events happen, you don't need this method. If you're seeing most of the events happen, you probably don't need this method, but if there's a fair number, then I think it's useful to see what you can learn from this. And our simulation results indicate that the traditional model gives very noisy results if there are important covariates that predict those who are event-free at tau, but otherwise, if they're not important covariates for that part of the model, you can still use tau RMST, the traditional model, and you'll be fine. And I do think that seeing regression results for the two different components of the tau IBR model can be helpful in understanding treatment effects. When you look at those different ways of what is it doing to the restricted mean, and then what is it doing to the event-free probability, you really get a different view of the impact, So I like that part of the model very much, seeing, where the differences are happening and
That seems like a real essential piece. Tease that stuff apart.
Yeah, I really do like, this is, the figure from the paper is all three panels at the same time, but this is, in this study, this is where everything's happening. It's in these probabilities of being exacerbation free. And regardless of the amount of time you're following, you're less susceptible during 3 months if you're taking azithromycin, you're less susceptible during, 6 months if you're taking azithromycin. It's pretty across the board that you're just generally less susceptible, but amongst those people who have the event, the covariates aren't predicting how much of that follow-up time you spend exacerbation free. So it seems to be that the action is here, and you don't see that when you look at just restricted mean time to exacerbation. You can look at this too, of course, but you don't see it as clearly. Why are the means different? Well, it's not because of what happens between 0 and tau, it's what's happening to keep people from being susceptible here. So I found this really interesting. I think I keep on telling my graduate student research assistants to use this method now, and I'm just realizing that my camera is like from underneath. I hate the underneath, like Jabba the Hutt view. But I do think that this is an interesting way to understand what's going on with your time to event data. And I think this neglecting the number of people that give you information that they did not have the event during the study period has just been really underutilized in understanding how things work. Mainly because with censored data, people are just, it just hasn't been an easy way to deal with it. And so that's it. Ended practically on time even.
Thank you.
You're welcome.
And next week or next month, we will have a little follow-up, you said, at exploring this.
Yeah, so next month, we have a speaker who's going to talk about this inverse transform multiple imputation that I used. But when you have bivariate event times, and she's really kind of, I think she's fixed this problem of bivariate survival estimation through the imputation approach. So I'm very interested in what she's done, and she's a great speaker, so she'll give a good talk. All right, now everybody have some pizza.
Stop recording at this point.
Yeah, I think as soon as I figure out how, I will.